Now we're going to discuss how to evaluate compensation in order to diagnose the presence of a secondary problem. So there are formulas that tell us if compensation is going on as predicted, or there is too much compensation or too little compensation. If everything is going as predicted by these formulas that we are going to discuss shortly, then this means there is no second problem. But if the compensation is not following that formula, is not following the rule, this means it's either too much compensation or too little compensation. Either way, this will be a second problem. So let me just give you an example. I'm just throwing numbers. If we have a patient with metabolic acidosis and his bicarbonate dropped from 24 to 10. So to compensate for that bicarbonate going down, what is the compensation? Carbon dioxide should go down. The question is, how far down? How far down? Let's say, I'm just throwing numbers. Let's say that the formula tells us that carbon dioxide should go down to 23 millimeter mercury. So a formula tells us that in metabolic acidosis, whenever bicarbonate is 10, to compensate for that appropriately, carbon dioxide should go down to 23, should drop from 40 to 23. That's appropriate compensation. Notice that by appropriate compensation, I do not mean total compensation, because we already deleted the term total compensation. But by appropriate compensation, I mean this. If carbon dioxide drops to 23, this means we don't have any other problem. So if the blood gases shows us that the carbon dioxide measured by blood gases is 25, what do you think? 25 compared to 23. 23 is the expected level of carbon dioxide. So bicarbonate is 10. That's a primary problem of metabolic acidosis. And we are checking the compensation. And the blood gases tell us that carbon dioxide dropped by 15 units from 40 to 25. So 25 is almost as predicted. And we allow a plus minus 5 range, plus minus 5. So when we say 23 is the expected, plus 5, 28, up to 28 is okay, down to 18 is also okay. So a carbon dioxide level of 25, that's okay. And our final diagnosis will be what? Will be compensated metabolic acidosis, period. Compensated metabolic acidosis, there is no other problem. But if the ABGs show us that carbon dioxide is 35, now compare 35 to 23. Compare 35 to 23. What do you think? It's much higher, much higher. So it's even higher than the 28, the plus minus 5 thing. So this means that the compensation is not appropriate, not following the rules. This means there is a second problem. Let's give it a name. And remember, the name of any problem has a first name, which is respiratory or metabolic, and has a last name, which is acidosis or alkalosis. So what's the first name of this problem? The first name is respiratory, because we are evaluating carbon dioxide level, and carbon dioxide is always respiratory. So we have a respiratory problem. In addition to the metabolic acidosis, we have a respiratory problem. What's the nature of this respiratory problem? The rules tell us that carbon dioxide should be 23. The compensating carbon dioxide should be 23. But now look at carbon dioxide. It is much higher than expected. Much higher carbon dioxide means what? Much stronger. Red team means what? acidosis. So we have a secondary problem of respiratory acidosis, a secondary problem of respiratory acidosis. So the final diagnosis will be what? Metabolic acidosis and respiratory acidosis. Metabolic acidosis and respiratory acidosis. On the other hand, if the patient's measured carbon dioxide by the ABGs is 15 millimeter mercury. So again, we are going to compare the 15 to 23. What do you think? Acceptable, within the range, within the expected range, 18 to 28, with an average of 23, or much higher or much lower? Actually, it's much lower. Again, if the compensation, when we evaluate compensation, and we notice that the compensation is not following the rules, not following the formulas, this means it is inappropriate, which means there is a second problem. Let's give it a name. So what's the name of this second problem? Again, the name of this second problem is a respiratory problem, because it's a respiratory issue, because it's altering carbon dioxide level. And in which direction? We expected carbon dioxide to be 23, but now it is much lower than expected. Lower carbon dioxide, weaker red team. Who is going to win? The blue team. So that's a secondary problem of respiratory alkalosis. So this is how we evaluate compensation. So it's time now to talk about these formulas. And do we need, these are the formulas. There is formula for each problem. There is a formula for metabolic acidosis. There is a formula for metabolic alkalosis. There is a formula for acute respiratory acidosis and chronic respiratory acidosis, and same-wise for acute and chronic respiratory alkalosis. How are we gonna memorize these? And the good news is you do not have to. You do not have to memorize them, not for your practice and not for the test, because I will provide you with the formulas. But even these formulas, they look too complicated. Is there a simpler form of these formulas? And the answer is yes, definitely. And even this one, I have a simpler form for these formulas, and this is the simplest form. Simplified formulas of compensation. Let me explain it to you, and we are going to discuss multiple examples of how we apply it. All these formulas, you notice that these formulas are expressed as fractions. Fractions and arrows. Arrows represent the direction of change. Going up means it's increased, going down means it's decreased. And these fractions are nothing but the Henderson-Hasselbalch equation, which is, and let me use a black color, kind of neutral, which is Miss Bayes divided by Mr. Acid. Remember, Henderson-Hasselbalch equation, ladies first. Ladies first. Always bicarbonate is in the numerator. Always bicarbonate is in the numerator. Always bicarbonate comes first. Why? Ladies first. That's Henderson-Hasselbalch. So in any fraction here, in any one of these fractions, the numerator is always going to be the change in bicarbonate. The numerator is always going to be the change in bicarbonate. And the denominator is always going to be the change in carbon dioxide. Okay? And we have a formula for metabolic acidosis, a formula for metabolic alkalosis, and for respiratory acidosis, we have two formulas: acute respiratory acidosis and chronic respiratory acidosis. Notice that in acute respiratory acidosis, because the kidneys have not yet kicked in and the compensation has not yet started fully, so the change in pH is really significant. See, it's away from the normal 7.4, whereas it's away from the normal 7.4. Whereas in chronic respiratory conditions, the change is minimal. Why? Compensation is very effective. So that's the difference between acute and chronic respiratory disorders formulas. Okay, so let me analyze the numbers. And let's take some examples. And remember this plus minus 5 confidence interval or allowance I told you about. Actually, it is plus minus 3 for bicarbonate changes and plus minus 5 for carbon dioxide changes. But for simplicity, I'm gonna unify it as plus minus 5. So it's gonna be plus minus 5 for all, whether we are checking bicarbonate compensating or we are checking carbon dioxide compensation. So let's take some examples. Let's take some examples and learn how to apply this formula. And let me start with the simplest formula, this one, metabolic acidosis. It's one going down and one going down. And let me explain this using the whiteboard. Let's analyze this ABGs. pH 7.3, carbon dioxide 30, or let's make it 29. Carbon dioxide 29, and bicarbonate 14. First step, look at pH. It's low pH. This means acidemia. And now we are looking for a acidosis problem. So we know that in acidosis, the lungs should hyperventilate. The lungs should hyperventilate to lower carbon dioxide. Let's look at carbon dioxide. Yes, it's going down. It's going down, same direction as pH. So the lungs are doing what they are supposed to do. So the lungs are okay. So this acidosis problem should be metabolic. So this is the primary diagnosis. Metabolic acidosis is the diagnosis that explains the current ABGs. In metabolic acidosis, the pH goes down, bicarbonate go down, and as a compensation, carbon dioxide goes down. But the question is now we need to evaluate, is carbon dioxide going down appropriately to compensate, or is it going too far down or too little down? How to do this? We need to evaluate compensation. And what's the formula to use here? It's the formula of metabolic acidosis, and the formula of metabolic acidosis is written as such. And in the test, by the way, because Canvas does not allow these symbols of arrows going down or up, so I'm going to write the compensation formula in this way: -1/-1. Which one refers to the change in bicarbonate. Bicarbonate, miss base, ladies first, is always comes first. So if I write down this formula in colors, so -1, that's for bicarbonate, and in the denominator, or what comes second, the -1 is the change in carbon dioxide. When I read the formula, I always start where the problem started. Again, when I interpret this formula, I always start where the problem started. And the problem is metabolic acidosis. So the problem started at bicarbonate. So this is how I read this formula. In metabolic acidosis, for every 1 unit drop in bicarbonate, there should be a compensatory 1 unit drop of carbon dioxide. Again, I repeat, in metabolic acidosis, for every 1 unit drop of bicarbonate, this is the problem, this happens first, there should be 1 unit drop of carbon dioxide. This is the compensation, and this occurs second. So let's calculate how many units has bicarbonate dropped. It dropped from 24 to 14. So bicarbonate dropped by 10 units. And this means carbon dioxide is expected to drop by 10 units. So the expected PCO2 is 40, which is normal, minus 10. So the expected carbon dioxide should be 30. The expected carbon dioxide should be 30. Let's compare this 30, this is the expected, with carbon dioxide in the blood gases. 29, what do you think? Close enough? Appropriate? Yes. So the final diagnosis for this condition will be compensated metabolic acidosis. Compensated metabolic acidosis. Now, let's say, for example, that the ABGs showed us a carbon dioxide level of 37. Now, if we compare the 30 to 37, so it seems that carbon dioxide is much higher than expected. Much higher, this means inappropriate compensation. This means a secondary problem. What's the name of this secondary problem? It's a problem that is making carbon dioxide much higher. Not much higher than normal, much higher than expected by the formula, because I'm evaluating compensation. So carbon dioxide with a carbon dioxide level of 37, it's much higher than expected. The expected is 30. To be appropriately compensating, you need to drop to 30. But you dropped to 37, and 37 is much higher than 30. Then you have a secondary problem of respiratory acidosis. And if carbon dioxide instead of 29 was only 20, and when you compare 20 to 30, 20 is much less, much lower than 30. Again, it's inappropriate compensation, which means there is a secondary problem, and here the secondary problem will be respiratory alkalosis, because you're making carbon dioxide weaker. You're making the red team weaker. Who is going to win? The blue team. So that's respiratory alkalosis. So this is how to calculate and utilize the formula. Let's take another example. And I think we have examples here in the PowerPoint. Let me take example 7. And by the way, let's make this 70. 70 will be much easier in calculation. So let's look at example 7. Let's read the story. A 24-year-old man is found unresponsive on the floor, soiled with vomit. He was seen 4 hours prior and appeared well then. So this piece of information tells us that we are dealing with an acute condition. We are dealing with an acute condition. So this is the reason why in any case, in any problem, you should have some information coming from the patient's history and physical examination. As with any test, like if you are interpreting an X-ray, we do not treat X-rays. Tell me something about the patient. If you're looking at EKG, tell me something first about this patient. If you're looking at blood gases, tell me something first about this patient. Well, I'm telling you that 4 hours ago, the patient was okay, and now the patient is unresponsive on the floor, soiled with vomit. Okay, let me know the blood gases then. This is the blood gas results. The pH is 7.34. PaCO2 is 70, and bicarbonate is 34. Okay, let me shift to the whiteboard. Okay, so let's walk through this problem. First is look at the pH. pH is low. This means acidemia. And we are looking for a case of a condition of acidosis. And the condition is acute, or first it's an acidosis. So we need to know, is it respiratory or metabolic? We notice here that pH is going down, but carbon dioxide is going up. So if we apply the Rome principle, I'm sorry, it seems that I forgot to write down the bicarbonate level. So let me get back to the PowerPoint. Bicarbonate level is 34. Okay, back to the whiteboard. So if we apply the Rome principle here, it seems that the pH and carbon dioxide are moving opposite to each other, respiratory opposite. Or we know that in any acidosis, the lungs should hyperventilate to lower carbon dioxide. But here carbon dioxide is not low. Here carbon dioxide is higher than normal, which means the lungs are not doing what they are supposed to do, which means the lungs are the problem, which means the primary diagnosis is respiratory acidosis. Respiratory acidosis. And the history tells us that this respiratory acidosis is acute. So we have a primary diagnosis of acute respiratory acidosis. And this explains the current ABGs. In acute respiratory acidosis, the pH goes down and carbon dioxide goes up. Now we need to evaluate compensation to know if we have a secondary problem or not. So which formula are we gonna use to evaluate compensation. It is the formula that says +1 + 10. The +1 describes the direction of change in bicarbonate. The +10 describes the change in carbon dioxide. And bicarbonate is always in the numerator. Miss base always in the numerator. Ladies first. But how do we read the formula? How do we interpret the formula? We always start where the problem started. Now this time, what is the primary problem? It's respiratory. So where are we gonna start? From the red side, the respiratory side, or from the blue side, the bicarbonate side? We are gonna start with the respiratory side because this is where the problem started. So this is how we read the formula. In acute respiratory acidosis, for every 10 unit increase in carbon dioxide, bicarbonate should go up by 1 unit to compensate for that. So now let's look at carbon dioxide. Carbon dioxide went up from 40 to 70, which means carbon dioxide went up by 70 minus 40. Carbon dioxide went up by 30. How many tens in this 30? There are 3 tens. For every 10, bicarbonate should go up by 1. So let me illustrate it in this kind of ladder thing. So normally, carbon dioxide is 40. But it increased by 3 tenths, from 40 to 50, from 50 to 60, and from 60 to 70. So that's 50, 60, 70. Now the normal bicarbonate, which is 24, when carbon dioxide goes up from 40 to 50, bicarbonate should go up from 24 to 25. And then when carbon dioxide goes from 50 to 60, bicarbonate should increase from 25 to 26. And finally, when carbon dioxide increases from 60 to 70, bicarbonate should go up from 26 to 27. So for these 3 tenths, bicarbonate should go up by 3 ones. So bicarbonate should go up by 3. So the expected level of bicarbonate will be 24 plus 3 will be 27. That's the expected level of bicarbonate. Now let's compare the bicarbonate measured in ABGs 34 and compare it to 27. What do you think? Close enough? Much higher, much lower? We notice that it is much higher than expected, which means inappropriate compensation, which means a secondary problem. Let's give it a name. This secondary problem is messing up with bicarbonate level. So this secondary problem must be a metabolic problem. Metabolic what? it's making bicarbonate much higher than the expected level. The expected level is 27. But this second problem is making bicarbonate 34. So to be appropriately compensating, bicarbonate should have been 27. But thanks to this second problem, bicarbonate is much higher than expected. So what is the process that makes the blue team much stronger, that makes bicarbonate much higher? It should be metabolic alkalosis. So the full diagnosis of this case is acute respiratory acidosis and metabolic alkalosis. Acute respiratory acidosis and metabolic alkalosis. So if we get back to the PowerPoint here. So which of these answers is correct? Which one is correct? And this is the correct answer. Respiratory acidosis and a second disorder of metabolic alkalosis. And we can find something in the history to support that. It's respiratory acidosis, and I should have put acute, actually. And it's because the guy is unresponsive. That's probably an overdose of something like opioid or something. And metabolic alkalosis because of the vomit. He vomited. Okay. Why is answer 4 not correct? Answer 4 also has metabolic alkalosis and respiratory acidosis. But the difference is answer 4 puts the respiratory acidosis as a secondary disorder and not a primary. And the primary disorder is metabolic alkalosis. And we agreed that the primary disorder is the disorder that accurately explains the current ABGs. So metabolic alkalosis, does it explain the current ABGs? The current ABG has pH, which is low. And this means it is acidosis and not alkalosis. Therefore, answer 4 is incorrect. But answer 2 is correct because respiratory acidosis, yes, it explains the current ABGs, pH going down, carbon dioxide going up, that's respiratory acidosis, and we add acute according to the history. And a second disorder of metabolic alkalosis because when we applied the compensation formulas, we realized that bicarbonate is much higher than expected, and that's a second disorder of metabolic alkalosis. And this is how we apply the compensation formulas to diagnose the presence or absence of a secondary problem. And this ends this segment.